Hello and welcome everyone. My name is Michael Horn, and today we will be doing two different problems. I have them briefly written down on the iPad here. You can see the first we will be starting with the Gibbs equality of Gibbs, and we will be deriving the Clausius-Clapeyron expression for vapor pressure working with a pure component. And then secondly, we will be using the Raoults law and that Clausius-Clapeyron equation in which we derived, and we will then be deriving conditions for which relative volatility is constant. So I'm going to take some time and I'm going to draw out a little figure for us to look at, and we'll get right into it. Okay, so we can first begin by drawing out just a figure for our component. As I said previously, it's going to be a pure component, so we will represent this by drawing a square here, and it is equal parts vapor and liquid. And then we also have our Gibbs free energy, so which we will say the Gibbs free energy in the vapor is equal to the Gibbs free energy in the liquid. And then finally, the last section we probably write down is that we will have changing pressure and temperature. So I've written a couple things down here that we're going to go over. First, just so we're aware, H is equal to enthalpy, the S is equal to entropy, and U is equal to internal energy. Now, as you can see right here, we have this equation which is equal to the Gibbs free energy, which is equal to the enthalpy minus the product of entropy and temperature. And then, right below it, you have the equation for enthalpy, which is going to be the internal energy plus the product of the pressure times the volume. So, first we're going to take this, and we are going to derive it. So you have dH equals du, and then with the product rule it becomes P dV plus V dP. And then we are also going to differentiate this equation, which will be dG equals dH minus T ds minus S dt. Now, from here, as you can see, we have this entire equation that we are able to plug into here. Now, after this is plugged in, you will arrive at the equation dG equals V dP minus S dt. So now that we have this equation, we are going back to this equation we have written above, which says dGV equals dGL. Now, we are able to substitute this boxed equation we have into this equation right to its right, and you will get V dP minus S dt vapor is equal to the same thing, VdP minus S dt liquid. From here, you're able to do some algebra, combine like terms, and you will get V vapor minus V liquid, all with respect to pressure, equals change in entropy with respect to time. So now we are just one more step from getting to the Clausius equation. As you can see here, delta S is equal to the delta H vap divided by the temperature with respect to dt. And so as you can see here, we're actually able to plug that in right there, and you will be resulted with the equation change in V EP equal to this. So now we have arrived at our Clausius equation, but we will need to do a couple more things to this to get it to be actually the Clausius-Clapeyron equation. So now we are going to move into the Clausius-Clapeyron equation, and as you can see at the top of the screen, we have our equation derived. We are going to rewrite it, and then I'm going to walk you guys through some of the assumptions as I'm writing it. So we have V minus VL dP Now, Clapeyron realized that since we are working with a high temperature and low pressure, that we are going to be assuming that this is an ideal gas. Now, due to this, we are assuming that the volume is so much bigger than the actual liquid that we are able to cross out this term here and assume it to 0. Now, secondly, since this is an ideal gas, we are able to know that VV is equal to RT over P. Now, once we substitute all of this in, we will go arrive to our next equation, which is RT over P dP equals H vaporization over T dt. Now our next goal is to be able to reach a point in which we are able to integrate. To do this, we're going to need to get all of our similar terms on one side. So we're going to move all of our t's to the right and all of our p's to the left. Since r is a constant here, we are able to isolate it, in which we will have r of 1 over p dp, and this becomes delta H of vaporization over t squared dt. So now we will start integrating this, in which you will get r times ln of p2 over p1 is equal to delta H vaporization times 1 over T2 minus T1. And then we will move the R over to the other side, so we will have ln P2 over P1 times H vap over R times 1 over T2 minus 1 over T1. So now, before we write our final equation, we do have to fix one thing. As you can see right here, there is a negative in front of the H of vaporization. And to fix this, we are actually just going to swap around the T2 and T1. So our final equation is, try to write it in very nice handwriting. P2 over P1 equals a positive heat of vaporization over our R times 1 over T1 minus 1 over T2, and again that's because we had a negative sign out front. So I will draw a nice red box around this and write out, this is our Clausius, I hope I'm spelling it right, Clapeyron equation. And now we will be moving into part 2 of this, which we will use this equation plus Raoults law, and we will derive the conditions for relative volatility when it is constant. Alright, I wanted to give a quick update. The room I was in apparently was reserved, so I just had to move my entire setup to this other classroom. Okay, let's get back into it. So, as you can see in the top of here, we have Raoults law. And Raoults law equation is right below, which is going to be xi pi equals yi pi sat. And now this right here is going to be equal to, sorry, I lost my train of thought. Oops, sorry. K1 over K2. Which then also would be equal to P1 sat over P2 saturation. And now final, this K value is going to be equal to yi over xi, which is equal to Pi sat over Pi. Now the final equation that we're going to need is obviously that Clausius-Clapeyron equation, which I will rewrite ln P2, P1 over R, T1 minus T2. Now, we are going to use all of these equations, and this will help us solve for the relative volatility to make sure it's constant when we are dealing with not just different temperatures, but different components also. So now we are going to rewrite this Clausius-Clapeyron equation to find the ratio of the pressures for multiple components at multiple different temperatures. And to do this, we're going to need to write two different Clapeyron equations. The first being log base, and this will be PB1. So this is pressure 1, but the temperatures are going to be B and A subscript. So this would be that, which will then equal heat of vaporation 1 over R. And now instead of T1 and T2, it is going to be TA minus 1 over TB. Now we're going to do the same thing, but now with component 2. So log of PB2, peanut butter. I wish. So it is essentially the same equation, but swap out all of the 1s for 2s. So at this point, a fair question may be, what are we even looking for? What is the purpose of this? And so just so everyone's on the same page, the point of this here is so that we can get two different temperatures, whatever we may want, TA and TB as I'm circling there, and we will see how it affects the ratio of the pressures in here. So again, by changing this, we will try to see how this ratio gets affected, and that is the purpose of this. The next step here is to modify these two equations that we have, so we are able to kind of put them together in a sense and to find the common point of where that relative volatility becomes constant and unchanging. And to do this, just so we are reminded, if you have a term like log, and let's say you have x over y, that is also equal to log of x minus log of y. And this is what we're going to use to help us solve this equation here. So as you can see, we have log PB1, oh, I'm sorry, I missed a 1 here. So as you can see, we have this PB1 over PA1, and what we're going to do is take this log of PA1 and slide it over there and add a plus sign because it is subtracting on the left, so we're going to add it on the right. So let's do that. So then we are left with log PB1 equals this. I feel like I've written this 100 times now. And A minus TB. And now we have this plus of log PA1. And now you'll do the same with the second equation, in which we will take this log of PA2 and slide it here and add a plus sign. So I'm going to try to make this a little bit quicker. Just copy this. And then just kind of erase this term. We'll do log of PB2. Then add a log of PA2. Alright, so now from here we are going to be able to sub these two equations into each other and solve for that constant. Now we are going to combine this all into one large equation, and I'm going to need a smaller pen size here. So as you can see here, we have these PB1 over PB2 and PA1 over P2, and we are able to make this into a ratio. So on the far left side, zoom in a little bit, we will have log PB1 over PB2. Yeah, you're able to see this. Now, this middle term, we're going to separate out by TB and TA. So the first one, we're going to multiply everything by 1 over TB. And then in the inside now is going to be HVAP 1 over R minus delta H vaporization 2 over R. And we will do this again. We will add this, but now with instead of TB, we're going to make this TA. And then our final term, don't know, I'm going to try to fit it. We're going to add log, this is going to be tight, PA1 over PA2. I know that's a little smushed right on the end, but this is our one total equation, and now from here we will continue searching for our constant. Now the final step is we're going to look into this equation and see, well, how can we make this constant, you'd be thinking. Well, to make this constant, you would want that log of PB1 over PB2, I'm going to use this. You want this to be solely dependent on this final term over here to the right, which means we have to find a way to neutralize everything inside those brackets right there. Now, the first thing that comes to mind is you would realize, well, if you set the vaporization of 1 equal to the vaporization of 2, since you're subtracting them from each other, that would make this equal to 0 and this equal to 0, and this would be completely scribbled out. So that's exactly what we're going to do. To make this relative volatility constant, you're going to need to find a place in which the heat of vaporization at phase 1 and phase 2 are equal, making them cancel each other out. So then you are left with this equation of the log of PB1 over PB2 is equal to the log of PA1 over PA2. Now again, the reason that this is constant is because it is solely dependent on the temperature of A and the temperature of B that you're choosing, and those can be any temperatures you want, which is going to mean that it's the same ratio and it is constant every single time, as long as, which this is the most important part, the heat of vaporization in 1 is equal to the heat of vaporization in 2. So this is our final answer here, and thank you all for following along.